Intermolecular forces. In this video we're looking at non-polar molecules, and that means London dispersion forces. Intermolecular forces are weak forces of attraction between molecules. The strength of intermolecular forces is London dispersion force is the weakest, followed by what we call dipole-dipole forces, and the strongest, hydrogen bonding. The type of intermolecular force depends on the polarity of the molecules. Bond polarity is caused by a difference in electronegativity. So, we can use electronegativity values to see if a bond is polar. Firstly, electronegativity is defined as the ability of an atom to attract electrons in a covalent bond. If one atom forming a bond has a higher electronegativity than the other atom, it will pull electrons towards itself, making the bond polar. If the electronegativity difference is above 0.8, then I consider the bond significantly polar. That's a rule of thumb that I find to be most helpful. Electronegativity increases across a period and decreases down a group. Here we see the elements in periods 2, starting with Li lithium in group 1, and in period 3, starting with Na sodium in group 1. Firstly, I see as I cross a period, electronegativity values shown in blue gradually increase in both periods. Looking down a group 1, lithium 1.0, sodium 0.9, a difference of 0.1. Group 2, the difference becomes 0.3. Group 13, the difference is 0.4, and it increases until I get to groups 15, 16, and 17, where my difference in electronegativity between the two periods is the biggest. We see that electronegativity becomes much more significant as we go across to the higher groups. The three elements with significantly high electronegativity values are highlighted. That's nitrogen, oxygen, and fluorine. The electronegativity of hydrogen is taken to be 2.2. For the IB, hydrogen only makes bonds that are significantly polar with nitrogen, oxygen, and fluorine, the ones that are highlighted in yellow. That creates hydrogen bonding, the strongest of the intermolecular forces. If a bond is polar, then the electrons in the bond will be closer to one of the bonding atoms. A dipole exists, with one atom having a slightly negative charge, indicated by the Greek letter delta, delta minus, and the other having a slightly positive charge. Bond dipoles can be represented by partial charges or vectors. In my first diagram, I see water, H2O. Oxygen, larger atoms than the small hydrogen atoms. Polar molecules. Oxygen has a much higher electronegativity than hydrogen. Hydrogen atoms, smaller, shown in blue. And so, bonds formed between atoms of these elements are polar. I see delta minus for oxygen, delta plus for hydrogen. The Greek letter delta is used to show polarity, and we can see that this causes attractive forces between molecules, shown with the red dotted lines. Beneath that, I see NH3, ammonia, nitrogen bonded covalently to 3 hydrogen atoms. In this convention, the pull of electrons towards the more electronegative element is shown by the red arrows. These are my vectors. So, in the first diagram, we see partial charges, which I prefer and find most useful. In the second diagram, I see vectors. we might expect polar molecules to have a higher boiling point than non-polar molecules because of increased attraction between molecules. They are more soluble in water than non-polar molecules because they will be attracted to polar water molecules. In fact, they have properties in common with ionic compounds. So, polar molecules do have properties in common with ionic compounds. The difference is that there is only slight attraction between polar molecules, but much stronger electrostatic attraction between oppositely charged ions in an ionic compound. So to recap, intermolecular forces are weak forces of attraction between molecules. The type of intermolecular force depends on the polarity of a molecule. Intermolecular forces will be stronger if a molecule has a longer chain of carbon atoms. Why? Longer chain of carbon atoms means more electrons, means more chance of an induced dipole. The strength of intermolecular forces is London dispersion being the weakest, then dipole-dipole forces, and hydrogen bonding. In the rest of this video, I will be focusing on London dispersion forces. Van der Waals forces is an inclusive term used for weaker intermolecular forces. That's everything except hydrogen bonding. So, dipole-dipole, induced dipole-dipole, and London dispersion. There are 4 types. London dispersion forces being the weakest, followed by permanent dipole to induced dipole, followed by permanent dipole attractions, and the strongest hydrogen bonding. London dispersion forces are induced dipole attractions and are found in all molecules. They're about 1% of the strength of a covalent bond. In a non-polar molecule or atom, at any instant there may be more electron density on one part of the molecule because of the random movement of electrons. We see that in the diagram above. Randomly, there may be more electrons at one end of the molecule compared with the other at one moment in time. Now, this would cause the molecules to have a slight positive end and a slight negative end at that moment. This causes an adjacent molecule to have a dipole, an induced dipole, as the positive charge in the temporary dipole attracts electrons in the neighboring molecule. Molecules now attract each other, and I see that in the diagram below. If I randomly have a dipole existing in one particle, the particle next to it will have the negative electrons attracted towards the slightly positive end of the first particle. Particle could be a molecule, could be an atom. The forces only act for a short time as the electron density is continually changing. These forces are continually switched on and off. But in a large sample, and we always have a very large sample of particles, there will be induced dipoles at some parts. Larger molecules have larger London forces as there are more electrons randomly moving. As group 7 is descended, I'm looking at the atomic number increasing as we go down. That means more protons, which in turn means more electrons. The halogens, fluorine to chlorine to bromine to iodine, and I see the boiling point gradually increasing. So, the halogens have increasing boiling points. There are more electrons moving randomly, and more electrons means larger London forces. It also explains why the boiling points and densities of the non-polar alkanes increases with the length of a carbon chain. The formula gives us the number of carbon atoms in that chain. I see the boiling point gradually increases as the chain gets longer, and state at 20 degrees C comes from there. Big difference between the densities of butane, 4 carbons, and pentane, 5 carbons, simply because pentane is a liquid because of the increasing London dispersion forces. Butane, the forces are small enough for it to remain as a gas at room temperature. With organic molecules, London dispersion forces are also larger if molecules are linear. If there's a lot of branching, then molecules can't line up so easily, and so less London forces can be established. I see that looking at 3 compounds which have 5 carbon atoms. Pentane has 5 carbon atoms in a line linear. I haven't put in the hydrogens, we know they're there. Methylbutane, we have a chain. Dimethylpropane, we have 2 side groups, 2 chains. And I see my boiling point decreasing as the number of side chains increases. London dispersion forces are always present between molecules. They are the only intermolecular forces between non-polar molecules. They're also considered to be present between molecules with dipole-dipole forces, but are negligible with hydrogen bonding present. Thank you. Hoping you got something out of that. If you did, please hit like. Please subscribe to be informed of more content.